Hello, this is Sadbir. The topic of our discussion in this video is the axiom of completeness of a real number. Before I give you the statement of what is the axiom of the completeness, let me go over some basic definitions and notions. Our first definition is what is axiom. Axiom. Axiom in mathematics is an accepted assumption to be used without proof. These assumptions in mathematics will be so obvious or it is so intuitively clear that we do not need any proof of uh, this assumption. For example, if I say that 1 plus 1 is equal to 2, because this is an assumption in mathematics that the sum of the 1 plus 1 is always equal to 2. And if this assumption is so fundamental that we don't need to prove that why the sum of 1 plus 1 is equal to 2. Our next topic is what is axiom of complete and why we need the axiom of completeness. In my first video, I showed you that if we have the real number, if we do not have the real number system, for example, assume you live in a world where only you have rational number, and as you can see that it was true in the time of the Pythagoras, because in the Pythagoras time they have only rational number. There was no real number in their time. So if you assume you live in a rational number system, and we know that in a rational number system, between two rational number there may or may not be a rational number, and I showed you that in the rational number system line, between 1 and 2, there was a some point here on the rational number line system where there was a hole in the rational number line system, and that was hole where that number square root of 2, which was not an irrational. So there is an issue with the rational number system. There are many holes. So this is a biggest limitation of a rational number system was because there was so many holes. And to overcome this issue, we defined a new real numbers or a real number system. And in this course, we will prove that there is no hole in the real number system. So there is no hole in the real number system. So this is a theorem which we will prove in our later coming up videos. And in order to prove this theorem, so we need an assumption. So we will make an assumption. We will need an assumption to prove this result. That assumption gonna known as, later we're gonna call that assumption the axiom of completeness. So the name of that assumption is the axiom of completeness. So this is the axiom of completeness. We will make an assumptions on real numbers, on a real number, and that assumption we will call the assumption of completeness. So since this is an assumption and this assumptions will be a fundamental assumption, so we will not prove that an assumption, or instead we will take this assumption as granted and we will prove that there is no hole in a real number system. Uh, Before I give you the statement of this axiom of completeness, I need a few definitions. So I will go over some basic definitions and notions before I give you the complete statement of the axiom of completeness. Our next definition is what is a bounded above set. A set a subset, a, a subset A of real number is called bounded above set if there exist, if we can find, if there exist a real number, a, a real number. I'm going to call this real number u. So let's suppose I can find a real number u so that the each element of this set is less than or equal to that real number u for all x in A. And that u is also has a name. That u is called upper bound of the set. Upper bound of the set. And that set A is called the bounded above set if we can find a real number u so that all the element of that set are less than or equal to that u. So let me give you few examples. So my first example, S1. Let's suppose S1 set, it has element 1, 2, 3, and 4. So this S1 set is bounded above. This is a bounded above set. The reason is that I can find u, which is a real number. For example, if I choose my u is equal to 4, and I can see that every element of this set, all the element of this set always less than or is equal to 4, no matter what element I choose from the set S1. So this is a short form of for all. So every element of the set is a less than uh, or equal to 4. So this is an upper bound. And also you can notice that if I choose u is equal to 5, this also work. So every element of this set is also less than or equal to 5. So 5 is also an upper bound. So in fact, a set can have infinite many upper bound. So for example, the list of upper bound of S1 is basically 4 is an upper bound, 5 is an upper bound, even 4.1 is an upper bound, 6 is an upper bound, 100 is an upper bound, 1000 is an upper bound, and so on. So a set can have more than one upper bound. Let's take one more example. This time my set is 1 over n, where n belong to the set of natural number. So this is a mathematically way a set has been written. So I can also write in a element notations. So the element of these sets are, as you can see, 1, 1 half, 1 third, 1 4, and so on. It has infinite many set in this set. And also I can list all the upper bound. So this is the list of upper bound of S2. So as you can see, 1 is an upper bound because every element of the set is less than 1. Similarly, 2 is an upper bound, 3 is an upper bound, 100 is an upper bound, 1000 is an upper bound, and so on. So there are infinite many upper bound of this set as well. Our next definition is a bounded below set. So a bounded below set, a subset A of R is called bounded below if there exists, or if we can find there exists a real number. This time I'm going to call that real number L. L is a real number. so that each element of the set is bigger than that real number. So every element of the set is bigger than that real number for all x belongs to A. And that number L which exists is called lower bound. The lower bound. For example, for the set S, S1 is an bounded below set also, and the list of the the lower bound. So if the list of lower bound for that sets are basically 1 is a lower bound of the set. Similarly, 0 is a lower bound, negative 1 is a lower bound, negative 100 is a lower bound, and so on. So it has also infinite many lower bound, and the few of them I listed it here. So for the set S2, which was I define here, the list of the lower bound. So we can list all the lower bound. The list of lower bound is as you can see that intuitively the 0 is an lower bound because 0 is the element which is every element of that set is bigger than 0. And also it is very interesting that this time the 0 do not belong to the set, but it is still a lower bound. And also negative 1, negative 2, and so on, negative 100. And there are infinite many lower bound of this set. So the next definition is going to basically coming from the idea of upper bound and lower bound, because there are infinite many of upper bound and lower bound, and we would be looking for a one specific lower bound and upper bound which is important for us. So our next definition is what is a least upper bound. If I have to write this definition in a simple wording, so I can write it as a least upper bound of a set is the smallest upper bound. The smallest upper bound of the set. So if you compute the list of the upper bound of the set, and then you have to pick the smallest among that upper bounds. For example, for the set S2, we have seen that 1 over n, that set was where n is belong to the set of natural number. The list of the upper bound were basically 1, 2, 3, 100, 1000, and so on. And as you can see that the smallest upper bound, if I have to choose the smallest one from this list, the smallest among is 1. So this one is we'll call the LUB of the set S2, or in other word, the least upper bound of the set. And this basically the notation for this LUB is also sometime you will see in the books or in the coming video is also sup. Sometimes it's defined as the supremum or in short the supremum. So sometimes it is a denote in a short form as the sup of the set. In that case, it is a 1. Also, you can see in the set S1. So if I have to write 1, 2, 3, 4, the sup of that set S1, as you can, is 4, because 4 is the least upper bound of this set. So this is the definition of the least upper bound. Now I'm going to give you a definition which is a bit more mathematically, and which we will use in our coming video more. So which is basically taking this definition which is written in a wording and write in more mathematically form. So here is the more formal definition of least upper bound. We say a real number S um, is called is called uh, and least upper bound of a bounded above set A if it satisfies these two properties. Number one is the S is an upper bound of A, or in other word, S is basically the always greater and equal to every member of this. And the second property is, so if you pick another upper bound, if you pick U, an arbitrary upper bound of A, an arbitrary upper bound of A, this will implies that S is the smallest than U. So S is the smallest upper bound, that if you pick any upper bound arbitrarily from that set, the list of the upper bound, the S is going to be always the smallest upper bound of that set. So similarly, you can also basically define what is a greatest lower bound. Similarly, just by using the definition of what is a bounded below set. But I would let you define these definitions by yourself. Here I have one quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. Now we have the definition of least upper bound of a subset of real numbers. Now I can give you the statement of what is the axiom of completeness. So the axiom of the completeness is basically tell us that every bounded subset, so we assume that the every bounded above subset of a real number has an upper bound. So in simple wording, if you have a which is a subset of a real number, and A is bounded, A is a bounded above, then there exists basically the soup of that set exists. That set exists. If I call that S, and that S is also a real number. So that assumption has been made that whenever we have the bounded above set, we will be able to always find the least upper bound of that set, and that least upper bound will be a member of a real number. So using that axiom, we can prove now this theorem. So I theorem I state that if the axiom of the completeness hold, so the axiom of completeness implies there is no hole in the real number system. So that is the basically power of this axiom is we can prove there is a no hole in the real number system. In coming videos, we will prove this theorem, and along with that, we will prove some more theorems, which we will see that by just assuming that the axiom of the completeness, we can prove many result in real analysis. Here I have one more quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. This is also the end of this video. Thank you very much for watching. I will see you in the next video.